Hello, this video is on lesson 7-1 where we talk about quadratic functions. Learning targets here are to formulate quadratic functions in a problem-solving situation and to graph and interpret quadratic functions. This lesson begins on page 103. Okay, so let's go ahead and jump into it. Fence Me In is a business that specializes in building fenced enclosures. One client has purchased 100 feet of fencing to enclose the largest possible rectangular area in her yard. Okay, so let's go ahead and highlight some important information here. 100 feet of fencing, and we want to enclose the largest possible rectangular area with those 100 feet. That is the main idea of this lesson. With 100 feet of fencing, what is the largest possible area that I can enclose? Alright, so let's take a look at number 1. If the width of the rectangular enclosure is 20 feet, what must be the length? Find the area of this rectangular enclosure. So it really helps if we go ahead and draw a diagram. There it is. And it tells me that the width is going to be 20 feet. Now, it says that the total fencing is 100 feet. And so that means I'm going to use all of it. So that means that the perimeter of this rectangular area is going to be 100 feet. I'm not going to have any left over or any unused. I'm going to use all of it, all 100 feet. Now, since this is a rectangle, since the width is 20 feet, both sides are going to be 20 feet. That means that the length of this is also going to be the same as this. Since I have 100 feet of total fencing, and I already used 40 feet, that leaves me with 60 feet left. And so since we are talking about a rectangle, the opposite sides are basically the same length. Take 60 divided by 2, and I find that my length is going to be 30 feet. Well, to find the area, I simply have to multiply length times width. And therefore, the area is going to be 30 times 20, and that gives me 600 feet squared. Okay, number 2, choose several values for the width of a rectangle with a perimeter of 100 feet. Determine the corresponding length and area of each rectangle. Share your values with members of your class. Then record each set of the values in the table below. Well, we already found one. We chose that the width was 20, and we found that the length equaled 30, and the area was 600 feet squared. Let's do another example. Let's go ahead and give 25 a shot. Okay, 25. And again, it helps if we draw a diagram here. So if we say that the width is 25, that means the other side is 25. So out of 100 total feet, I used already 50. And that means that I'm going to have 50 feet left over, which has to be divided by 2. And so it turns out that my length is going to be 25 as well. Now, you may say, but if the length and width are the same, then I don't have a rectangle. I have a square instead. Yes, you will have a square. But by definition, a square is also considered a rectangle. So any square that you have is considered a rectangle, and so this does a width of 25 and a length of 25 is considered a rectangular enclosure. Now we can go ahead and multiply these together. to find our area, 25 times 25, and that gives me 625 feet squared. Okay. And basically, you want to keep on doing this. Just discover different dimensions. And again, you want to keep this in mind. What is the largest possible rectangular area? Well, right now it looks like it's going to be 625. Is there something higher than 625? So keep that in mind as you are looking for different lengths, different widths, and the corresponding length and area. Alright. Number 3. What is the relationship between the length and width of a rectangle with perimeter of 100 feet? Well, let's take a look at this. And let's go ahead and do one more. What if I make the width to be 1 feet? Okay, well, let's take a look at a rectangle. And let's see here. So if I have a rectangular enclosure where the width is 1 foot, so it's 1 foot, okay. 1 foot on both sides. That means that out of 100 feet, my width has just taken up 2 feet. That means that I have 98 feet left to make up the length. Divide that by 2, and it turns out that the length, if the width is 1 foot, the length has to be 49 feet. Well, when I multiply the length and the width, it turns out that I have 49 feet squared, which is a very small area. So it's interesting how you still have a perimeter of 100 feet, but the areas can be so different that the smallest it seems that we can have is 49 feet squared, and the largest, what looks like to be the largest, is 625 feet squared. Now take a look at each of these widths and lengths. Do you see a pattern going on here? What is the relationship between the length and the width? So here we have a width of 20, here we have a length of 30. Width of 25, length of 25, width of 1, with length of 49. What happens if we add each of these length and widths, add them together, and notice that they all equal to 50. By the way, here it's basically asking you what the equation for the perimeter of a rectangle is. Well, simply, if my width is 20, then I have to multiply that width by 2 and add it to the length, which I have 2 lengths, and that should give me 100. That's basically the relationship. Based on your observations, predict if it is possible for a rectangle with perimeter of 100 feet to have each area. Explain your reasoning. So let's just go over the first one. 400 feet squared. Okay, well, first of all, my smallest area was 49, and then I have my next area is 600. So if I have 49 and I go to 600, then it must be possible for me to have some sort of dimension where my area is going to be 400 feet squared. Can you think of the dimensions? Well, I asked my students and they were able to come up with one. Well, what if my width was 20? Actually, you can go ahead and experiment with that. What length and width is going to give me an area of 400, but you have to keep in mind that the perimeter has to equal 100 as well. Okay, so that's how you do number 4. Number 5, let L represent the length of a rectangle with a perimeter of 100 feet. Write an expression for the width of a rectangle in terms of L. write an expression for the width. That's basically what you want to do. In terms of L, okay, so we want to know what W is equal to, and we're going to use this right here. 2W plus 2L equals 100. And basically what you're trying to do is solve for W in terms of L. The 100 here stands for the perimeter, and so it's basic algebra. In order to solve for W, well, first of all, we have to move the 2L to the other side, and so we have to subtract minus 2L on both sides, or I can write it right here, minus 2L. So that is going to become 0, and what I have is 2W is equal to 100 minus 2L. Next thing we need to do is divide by 2. Make sure we divide the whole thing by 2. And what we're going to get is W is equal to 100 minus 2L divided by 2. Now we can simplify this, and this is basically going to be 100 divided by 2 minus 2L divided by 2. 100 divided by 2 is going to be 50, and then negative 2L divided by 2, well, that's going to be minus L. And so here it is. W is equal to 50 minus L. So what did we do? We wrote an expression for the width of the rectangle in terms of L, basically telling me that in terms of L, my L is my independent variable. That's basically what it's saying, which is what we have here. Number 6, write and express the area A of L for a rectangle with a perimeter of 100 feet as a function of its length. Okay, so first of all, A of L represents the area. And how did we find the area? Going all the way back, area is equal to length times width. And so let's just go ahead and write that. Length times width. Now, so it says to express the area A of L for a rectangle with a perimeter of 100 feet as a function of its length. What does that mean? Function of its length? That's basically telling me that my input, my independent variable, is going to be L. So can we go ahead and just write this instead? L times W? Actually, we do have L. Here's my input of L. But this is not acceptable because what is W in this function? Well, first of all, L tells me that whatever's in parentheses is going to be my independent variable, which is L, and then this capital letter A, well, that tells me that's my output, which represents the area. In this function notation, is there a W anywhere here? Nope. So we cannot have a W here. So what do I do with it? Do I just get rid of it, erase it, and would this be my function? Well, area does not equal L. Area equals L times W. And so we need to replace this W with something. What can I replace it with? Well, take a look. Take a look at this. W is equal to 50 minus L. So, couldn't I just go ahead and replace W with 50 minus L? And now, does this make sense? Did I write a function where the independent variable is L and only just L? Here I have L here, and I don't have W anymore. I have L again. Yes, this is what I want. And we can go ahead and simplify this. A of L is equal to where we distribute the L, so we have 50L, And then L times negative L, well, that's negative L squared. There we go. A of L is equal to 50L minus L squared. That is my function, as this is the function A of L, where the independent variable is L, which stands for length, and the output is the area. Okay. Graph the quadratic function A of L on the coordinate grid. What you can do is you can take these, notice that our length is going to be my independent variable and my area is going to be my dependent variable. That means I can take these ordered pairs right here, treat them as ordered pairs where I have length and then the area, and put them on the graph. So 30 and 600, 30 and 600, here's my first ordered pair, 30 and 600. And we can keep on doing this. You should have this table full. So our next values is 49 and 49. So 49 and 49 should be somewhere around here. Let's see, what else do we have? 25 and 25, 25 and 625. So that's 650, 625, somewhere right here. And actually, when you start filling these out, you can start seeing, you can start using the other values to graph this. So if we have a width of 10, my length is going to be 40, which gives me a area of 400. So 40 and 400, 40 and 400, there we go. Now notice, what if our length was 30? Then the width would have to be 20, and we have 600 feet squared. And what if we used a width of 40? Well, a width of 40, then my length is going to be 10, and my area is still going to be 400. So notice that you can switch these, the length and the widths, and it's still going to give you the same area. And so if 30 and 600 is going to be on there, then 20 and 600 is going to be on there. And if we have 40 and 400, we're going to have 10 and 400. And if you keep on doing this, the resulting shape that you get looks like this. Let me try that again. It looks like this. Has to go through that point. There we go. Close enough. Now, what shape does this look like? It looks like a parabola, which is the shape of a quadratic function. Technically, it's a curve, not a shape. So what does this curve look like? It looks like a parabola. Okay. Now notice, do we want our line to hit exactly 0, where we have 0 length and 0 area? Again, we're relating this to the real world. Is it possible to have a rectangular enclosure where your width is 0, which means that your length is going to be 50, but then your area is going to be 0? No, this does not make sense. So notice, if we have a width of 50, that means that my length is going to be 0, and 50 times 0, well, that gives me an area of 0 again. So we don't want our width or length to be 0 or 50, which means that I'm gonna not be touching the x-axis. Instead, I'm just gonna leave open circles there. Okay. Now, use a graphing calculator to graph the quadratic function a of L. Set your window to correspond to the values on your axis on the graph in item 7. Okay, so let's go ahead and take our graphing calculator. And the function we're going to be using is the function that we have in item number 6. So instead of using 50L minus L squared, we're going to use 50x minus x squared, since that is what what our calculator recognizes. So let's go to the home screen, hit on the graph, and remember our function is going to be 50x minus x squared. Go ahead and hit enter. Now what does this look like? It looks like a straight line. Doesn't look at all like a parabola. So here is something that we have to keep in mind. Sometimes the graph is so big that whenever you graph it, you only see this part right here, which is what our calculator sees. It sees a straight line. So we need to adjust the window settings in order to see the whole entire parabola. And notice that we go from 0 to 50 in our length, and then from 0 to somewhere around 700 for our area. So that's what we want to change. Let's go to menu, window zoom, and go to window settings. Now our x minimum is going to be 0, my x max is 50, x minimum is 0, and my x max was somewhere around 700. Hit OK, and there we go. That is exactly the shape that we kind of have here. So take a look at that. Number 9. Use the function a of L and your graph from items 7 and 8 to complete the following. What is the reasonable domain of the function in this situation? Express the domain as inequality, as an inequality interval, and interval notation and set notation. Okay. So something about this reasonable domain, that's what I was referring to when I talked about these open circles. Do I want my width to equal 0? Do I want my length to equal 50? And vice versa. Do I want my length to equal 0 and my width to equal 50? No, because we get an area of 0, which we don't want at all. So how does that affect our reasonable domain? Well, that basically means that we want an area where we have a non-zero number and a non-negative number. And so reasonably, we want our area to be greater than 0 and to help us find the maximum area. So if we want to, we're talking about reasonable domain. First of all, if we're talking about domain, we're looking at the horizontal axis, which in this case is the L axis. And so between what two values is my graph going to be stopping at? Is it going to keep on going forever? No, it's not going to keep going on forever. If it were, my graph would go like this and my graph would go like this. But remember, you don't want your length to go past 0. And so it's going to stop right, my elevator door is stopping right here. And I don't want to go past 50 or make it equal 50, so my elevator door stops right there. And so if I were to write the length, first of all, I have to write the variable. My smallest value is going to be 0, and my largest value is 50. Since I have it set up this way, all I have to worry about is if I'm going to use greater than or equal to. In this case, since at both ends I have an open circle, that means that my inequality is going to be greater than. Okay, so we just expressed the domain as an inequality. Next thing we want to do is interval notation. Again, This is going all the way back to lesson, I forgot what lesson we talked about domain and range, but it was a previous lesson. And whenever we have less than, we use parentheses. When we have less than or equal to, we use square brackets. In this case, we have less than on both sides. That means, first of all, I want to write my smallest value, comma, followed by my largest value. And since I have this less than here, I'm going to have parentheses by the 0. And since I have this less than here, I'm going to put parentheses by the 50. And so this is my interval notation. And finally, set notation. Set notation is also fairly easy, where we have to use square braces, curly braces, I mean, L such that, and then we just put our inequality. But something about set notation is, yeah, we want to include the whole inequality here. So 0 is less than L, which is less than 50. There we go. There's my set notation. Over what interval of the domain is the value of the function increasing? Over what interval of the domain is the value of the function decreasing? So just take a look at your graph in order to determine that value. 10. What is the maximum rectangular area that can be enclosed by 100 feet of fencing? Justify your answer. So you can look at the table. What was the highest possible area that we got from our table? Well, it looks like it was 625 feet squared, which meant that I had a length of 25 in order to get that maximum area. Let's take a look at our graph. 25, a length of 25 is right here. And notice that the area that you get is going to be 625. And as you can see, that ordered pair is right here. 25 and 625. Now, what do you see about this ordered pair when you put it on the graph? That ordered pair seems to stand on the very top of the parabola. It's the highest. It's the highest point of the parabola. So, looking at the graph, the maximum seems to be at where the length is 25 and the area is 625. And so just go ahead and justify your answer using this reasoning or looking at what we just looked at here. Okay, number 11, what is the reasonable range of A of L in this situation? Again, we already talked about the domain. Domain is just looking at the largest and smallest values for the horizontal axis. Now, what you want to do to find the reasonable range is, again, use the concept of elevator doors. Again, I don't want to have an area of 0 or go to a negative area. So my elevator door is going to stop right here. And notice that my graph at the highest point is going to be what looks like to be 625. But how do I know that is actually my highest point? Couldn't it be 625.1? Well, that's where we use our calculator. So we want to use our calculator to determine if that is in fact the highest point. So we go to Analyze Graph, and notice this graph has a maximum point. And so that means we're going to hit maximum. And once you do that, you're going to, you have this vertical line, you're going to click right close to where you think the maximum is at, click, and then drag it And once you drag it, it tells you what the ordered pair of the maximum is. And so indeed, a length of 25 gives you the maximum area of 625. So that answers this question. With 100 feet of fencing, the largest possible rectangular area is going to be where my length is 25 feet, which gives me an area of 625. There we go. So, to just write the reasonable range, again, just writing the inequality, we want to use the variable capital A. My smallest value is going to be 0, but we don't want the area to equal exactly 0, so we have to use less than. And we just found this out, that my maximum area is 625, which can be equal to 625, so we do need that symbol right there. Okay. Reverse or confirm your predictions. Okay, so this is going all the way back to question number 4, A, B, and C. What are the length and width of the largest rectangular area that can be enclosed by 100 feet? Well, we basically already answered that. The length you gave in item 13 is the solution of a quadratic equation in terms of L. Write this equation, explained how you arrived at this equation. Okay, so I encourage you to do number 15 as well. That one as well. This is an interesting question. And then take a look at that. Alright. That is lesson 7-1. Thank you for watching.